machine learning methods to learn them. And we need some different approaches. And this is particularly relevant for cases when those uncertain quantities are preferences of humans. So we might observe the choices that they make, but we want to recover the distributions over their preferences and how those vary with context. Our approach works because we use the score function gradient estimator. And for our problem, or for these choice problems, it has low variance or lower variance. And it's low enough to be able to use it for learning in this context. And the other important thing to take away is that our learn model is a generative model. So we can use it to generate scenarios in unseen contexts. And scenarios is often what you need to solve a variety of kind of OR problems. And like I said, we're going to use ride sharing as a motivating example of one of these problems. Um, but there could be other situations where you would want to generate scenarios. Uh, the ride sharing example comes from my experience founding a company called Blaze Transit, which is what I was doing before I started my PhD. And it's an illustrative example. It's meant to be used as one of these situations where you can observe uh, human choices, but not the kind of costs that are influencing those choices. So, for example, ride-sharing platforms will often recommend routes based on the shortest time, based on some real-time traffic information, but drivers won't actually follow those routes because they're optimizing a different objective function. And this could be based on tacit knowledge of the road network or something else. But when they don't follow the prescribed route and we make choices that or that we base that base downstream decisions on the assumption that the drivers are going to follow that route, it introduces uncertainty and leads to, in this case, a poor user experience. So this is the kind of really simple example that I came up with where we have two drivers and two riders. And the shortest paths from the driver A to rider one and driver B to rider two is 5 seconds and 6 seconds. And we're going to assign them based on their shortest path. So we're going to assign driver A to rider one and driver B to rider two. However, in reality, there's a small chance that, for example, driver A takes a different path, which would end up getting them to the rider. It would take them twice as long to get there. And the same story with rider B. There's a small chance they would take, or there's an equal chance in the case of rider B that they would take a different path to get to rider two, and this would result in them arriving later. So in this situation, when we assign drivers to riders based on the shortest travel time, they always end up getting there late. And this obviously is bad for the customer's perception. So you might be thinking, well, what if we just learned from the driver's routes and then we estimated the expected travel time based on what the routes that they actually take? Uh, this isn't enough either, because if we make a point prediction, in this setting, we end up with the same assignment, but there's still that variance that's introduced by variations in driver preferences. And without taking that into account, we still never the driver never seems to arrive on time. So either they arrive early or they arrive late. Uh, and this is bad again for the customer, but also the driver. If they arrive early, they feel like they're sitting there unproductively waiting, or they feel like the passenger is late. And this is something that we want to minimize in a ride sharing service to improve the user experience. what we would like to be able to do is to minimize both the expected travel time of the assignment problem and also that variance. So this is a risk-averse kind of formulation that we would like to do because it will result in, yeah, it'll minimize that variance and it'll result in the perception that the drivers are on time. And we have sort of a tunable trade-off. By tuning the risk tolerance, we can tune the trade-off by how much we want to reduce the expected travel time and the variance. So this is the kind of problem that we would like to be able to solve, but it requires recovering the distributions of the driver's preferences. So it requires not only it requires full distributional information to be able to minimize the risk. So the framework that we use to capture these preference distributions is a perturbed utility model. And in perturbed utility models, we assume that individuals make a choice by solving this integer linear program, where the U defines some utility of the different decision variables, and the individual maximizes there makes a utility maximizing choice. So these perturbed utility models generalize discrete choice models and also root choice models and other lots of other sort of choice modeling methods. So they're very general. Um, but we also have said that for an individual, the utility that they perceive depends on some context, like we mentioned before, which is represented by this matrix X. And the objectives between individuals in the population are heterogeneous. So they're drawn from this distribution PU given X. And this is the preference distribution that we want to recover with our method. So yeah, I'll give you an example that's specific to ride sharing. This is a screenshot from sort of the synthetic environment that we did our experiments in that we'll talk about more about later. But basically, we generate some context matrix, and based on that context matrix, it creates a utility distribution on each one of these edges in this little grid network. I'm not sure if you can see it, but the width of the arrow corresponds to the scale of the utility distribution, and the color corresponds to the location parameter of that distribution. But we can't observe the utilities because they're in the driver's heads. What we do observe is the choice probabilities that a driver will select a given edge going from their origin to their destination. So we actually observe the average choice probabilities, meaning that in a given context, we observe multiple choices made by different drivers. And this is common when the context includes categorical variables like the day of the week, or is rainy or is freezing rain. These are like binary or categorical variables where it's feasible that we would observe multiple instances of the same choice problem for corresponding to different utilities, but the same context. And basically, we average all of these together and we get this average choice probability. And this is the data that we have to learn from. Like I mentioned before, what we want to do is learn a model mapping these contextual features or this context matrix X to utility distributions. So we want to approximate that true utility distribution with some model Q theta. And the way that we're going to learn that model is we're basically going to simulate the choice probabilities under our learned model or under the predicted utility distribution and train them to match the observed choice probabilities. So this is a sounds simple, but the problem is that we can't backpropagate through this choice problem, as in many kind of decision-focused learning um, settings. We want to update, based on our loss, we want to update the parameters of our utility distribution, but this requires computing a gradient kind of across the choice problem. And the approach that we're going to use is the score function gradient estimator. A lot of existing kind of approaches to do this in decision-focused learning only you can only use them to learn the location parameter or like the expectation of the utility. But we need to do more than a point prediction. So this is where the score function gradient estimation comes in. So we have this moment matching objective in one, which is the loss. And to compute a gradient with respect to the distribution parameters, we use the score function gradient estimator, which is this section. It's very powerful because it can estimate a gradient for a distribution with any gradient with a tractable score function, which includes a lot of parameterizable distributions like normalizing flows. The problem with it is that it can have very high variance, depending on the function that you're kind of backpropagating through. In our case, the function that we want to backpropagate through is the choice problem, and the choice probabilities are bounded in 0 and 1, and this greatly kind of tightens the variance, or it greatly reduces the variance of the gradient estimator, such that it's feasible to use it for learning. And in our experiments, we compared to another score function gradient based method that's basically reinforced for decision focused learning. And while this method required post hoc gradient reduction techniques, in our experiments, our method didn't require these. So that's sort of supports the claim that the variance in this for learning this problem with this estimator is much less. So moving on to the kind of inference problem. Once we have our learned model, we can't use it to evaluate the probabilities of taking a path directly, but what we can do is use it to generate scenarios. And that's often the way that we want to solve the problem anyway. So in this sort of diagram that I've made, we can see that there are supposed to be four sampled scenarios here. For example, from DA to R2, in every scenario, we sample one single path, which corresponds to the probability of, we're going to have a probability of one of taking that path. But for example, from DB to R2, there's an equal probability that we take the path to the right or to the left. So we get two samples on the right and two samples on the left. And this is how we're going to solve our risk-averse assignment problem. So coming back to our synthetic benchmark, we have this training data set that I mentioned before. So we have the context X and the corresponding choice probabilities. And we train our model based on this. And now at test time, we want to solve this assignment problem using our learned model. So we're going to get an unseen X, and we want to predict the edge utility distributions for this grid graph. And we're going to use those to solve this assignment problem with randomly kind of distributed drivers and riders. To do that, we're going to use the model to sample from the edge utility distributions and solve shortest path problems or maximum utility path problems, I should say, between each rider or driver pair. And that'll allow us to assemble that into kind of a cost matrix scenario. And we're going to generate a lot of those scenarios and solve a CVAR minimizing objective to compute our final rider driver assignment. And the way that we're going to measure the performance of the model is with this post-decision surprise metric. And that measures the difference between the kind of arrival time as predicted by our model, or it measures the difference between the arrival time given the assignment, given the scenarios that were generated by our model, compared to that same assignment with the real edge utility distribution. So what the drivers would actually do in practice. And we're going to penalize, it's a two-sided metric, so we're going to penalize arriving early and arriving late because both of those were undesirable in this kind of setting where we want to improve the user experience. We compare our approach to some other methods that are able to generate scenarios. So reinforce this is reinforce applied to decision-focused learning, and it's the other score function gradient method. But it doesn't have this property where it still suffers from this high variance problem. We compare it to maximum entropy inverse reinforcement learning, which treats the kind of driver route selection problem as an MDP. So you can generate rollouts to create scenarios. And then these last two, DPO and AIMLE, are decision-focused learning methods that are based on perturbations. So we can use those perturbing distributions to generate scenarios, but unlike our method, the scale of the distribution is fixed. They only learn the location, whereas our method can learn any number of parameters of the underlying distribution. And finally, we also compare it to a risk-neutral baseline with perfect point predictions. So even if you could predict the expected driver preferences perfectly, and you solve the risk-neutral problem, this is the last baseline. So here's the results slide. We vary the number of training instances and the number of kind of individual choices that we observe in that context. So I is the number of instances or the number of like contexts you can think of it as, and S is the number of individual choices that we observe in that context. So we go from very little data on the top left to a lot of data on the bottom right. In general, all the models perform better when they have more data, which is not too surprising. So the test loss measures basically how well the models reconstruct the observed choice distributions. And on the right, we have the post-decision surprise, which is the metric that I just described. With very little data, the other baselines don't actually outperform the risk-neutral baseline on average. Ours does, which is great. But when we add more data, so once we get up to 1,000 instances or 1,000 different contexts, the other methods start to perform better as well. And yeah, so that was our method to learn context-dependent utility distributions from observed choices. And it worked because the score function gradient estimator has a low variance in this setting. And the great thing about one of the great things for solving kind of these more practical problems is that our model can generate scenarios, which is applicable to more than just a risk-averse formulation. That, but this is what we used in our experiments. So.